2,000 years ago, a Roman merchant ship was sailing across the Mediterranean Sea when something went wrong. Just off the western coast of Sardinia, the boat sank beneath the waves, condemning its sailors and cargo to the sea floor. On board, there were plenty of clay jars, dishes, and other artifacts, maybe a Roman ghost or two, but the ship's real prize was more than 30 metric tons of lead that had been processed into 1,000 ingots. And while the ingots' original destination has been lost to history, their story was far from over. These bars were destined to serve a purpose far greater than anyone in the Roman Republic could ever conceive. Without the loss of that cargo, we'd be unable to run an experiment that hopes to answer fundamental questions about reality. Because in the 21st century, that shipment of ancient Roman lead is protecting the coldest cubic meter in the known universe. A cubic meter where scientists are hunting for what might be the rarest event in particle physics. If they find what they're looking for, we might finally understand the outcome of a cosmic war that ended 13.7 billion years ago. This is a very weird but true story of two different fields of science, archaeology and cosmology, colliding. I'm here to tell you how this ancient Roman shipwreck could help explain why you and I and everything else in the universe are here at all. Our story begins just a bit after the Roman Empire crumbled to pieces, when neon leg warmers were in fashion and Who Framed Roger Rabbit was the highest grossing film at the North American box office. People loved that movie. It was 1988, and about 10 kilometers off the Sardinian coast, scuba divers were investigating the seafloor, searching for shipwrecks and the artifacts that they might contain. In doing so, they stumbled upon an ancient treasure. 28 meters beneath the waves, hidden among the sand and seaweed, they spotted the unmistakable outline of a ship. And from the looks of the clay jars on board, it was Roman in origin. Now, Roman shipwrecks are actually pretty common throughout the Mediterranean. At their height, both the democratic Roman Republic and the subsequent Roman Empire dominated the sea's European and African shores. They laid claim to every harbor from Gibraltar to Turkey, and when you're that big, you're gonna lose a few boats. This particular shipwreck was found 2 kilometers east of a tiny island called Mal di Ventre, which might amuse some of you Italian speakers out there because it translates to stomach ache. But that's actually a likely mistranslation from the original Sardinian name meaning bad winds, which may contribute to stomach aches and also to shipwrecks. For more information though, archaeologists needed to take both a figurative and a literal plunge, and that is when things started to get interesting. After 2,000 years, the sea had destroyed much of the ship's perishable parts, including most of its original wooden structure. But around 10 meters of the keel had been buried below the sandy seabed, and plenty of erosion-resistant metal and stoneware had survived as well. From these pieces, investigators could tell that the ship was much bigger and much beefier than most of the others that had been found around the Mediterranean. It was a Navis Honoraria Magna, a class of sail-driven merchant ships that measured about 30 meters long and 9 meters wide. For comparison, that's about the same size as 9 school buses parked in a 3x3 grid. It was huge. At one end of the wreck, archaeologists found items that the crew likely used during their journey. There were jars used for storing food, as well as water and wine. There was also a millstone, which the vessel's sailors would have used to grind their own grain in the middle of a voyage. But in the center of the wreck, there was an even more remarkable find. The ship's cargo included 1,000 lead ingots, stacked as neatly as they would have been 2 millennia ago. Each of these ingots was roughly trapezoidal in shape, measuring 45 centimeters in length and 10 centimeters in height and width. In other words, like roughly the length of your hand and forearm together. But because lead is so dense, these metal blocks were 33 kilograms a pop, or about the weight of a 10-year-old child, or like a German Shepherd, or like a 50th of a Kia Sorento. So with more than 1,000 of these ingots on board, this ship was lugging around a shipment of lead that weighed over 33 metric tons. And that explained why the wooden hull had been strengthened in some places with nails up to 80 centimeters long. Now, to an ancient Roman, lead was kind of a big deal. Along with their Greek neighbors, they mined and smelted so much of this stuff that evidence of this industry can be found as a layer of pollution in ice cores thousands of kilometers away in Greenland. It was actually one of the first metals that humans learned to extract from an ore, in this case a mineral called galena, and it has a lot of properties that make it worth figuring out how to extract it. Lead is soft and easy to work with, but at the same time, it is durable and doesn't corrode easily. Plus, galena is also full of silver, which has its own uses, so even if you're trying to mine for silver, you end up with lead as a byproduct. Bonus. In fact, Rome had such easy and abundant access to lead that at one point, policymakers had to step in and restrict how much was being produced. But despite that abundance, before the Mal di Ventre discovery, archaeologists had only managed to find a few lead ingots on shipwrecks scattered around the Mediterranean. So this find instantly became the biggest load of ingots ever recovered from the ancient world. Professor Donatella Salvi, one of the lead archaeologists who investigated the wreck, told us in an interview that the discovery was of huge importance to Roman studies. By studying the unique construction of this merchant ship, which had been specialized for carrying such heavy loads, we can learn a lot about Roman engineering. But what about the lead itself? Unfortunately, we cannot know for sure exactly what the Romans had planned for this particular shipment. The metal's physical properties made it useful in a wide variety of products, coins, anchors, and slingshot ammunition, to name a few. Romans even used lead to line their aqueducts and build a network of water pipes that brought a reliable source of water to an enormous territory. That probably made the water somewhat toxic sometimes, but give them a break, it was 2,000 years ago, and we were using lead in water pipes not that long ago ourselves. We might not know what these ingots were destined to become, but there is something we do know just by looking at them. Each one bears an inscription stamped on the top of it. And while that text might seem to us to be a nonsensical string of letters, it is actually telling us who cast it. For example, this one is shorthand for the Societas Marci et Caio Pontianorum. In other words, it was made by a company owned by two Romans named Marcus and Gaius Pontanellius. Their company produced the majority of the ingots in this shipment, over 700 of them. And a subset of those ingots are also stamped with the letters PILIP, which researchers believe is a tribute to a deceased servant called Philippus. Meanwhile, there are a bunch of stamps corresponding to other men in the lead manufacturing business, like Quinto Appio and Planio Rusino. Professor Salvi told us this is invaluable information that paints a picture of both the entrepreneurs of the time and the powerful families that were involved in metal mining and trade. Together, these ingots tell us about how the Roman Republic managed its mines within its territory, that they were run by private individuals as opposed to being directly run by the state. The inscriptions also help us narrow down exactly when this ship made its final journey, because the names that the manufacturers use tell us that they identify as Roman citizens. And that was only possible when urban Italian tribes got representation in the Roman Republic. We know when the law that granted them that right was passed. It was 89 BCE, so we know the ship must have met its fate sometime after that. And yet there are still a lot of pieces missing from this 2,000-plus-year-old puzzle. Salvi says that archaeologists don't know where this shipment was headed, whether a delivery of this size was a one-off or a regular occurrence, and ultimately what caused the ship to sink. But because the ingots were still neatly stacked on the remains of the hull, the ship must have sunk straight down. And there didn't seem to be any major damage to the hull either. So it's possible that the region's famously bad winds could have destabilized the heavy load, causing the ship to take on water and dip beneath the waves. But some archaeologists think there is another possibility. During the 1st century BCE, the Roman Republic was in turmoil, with several civil wars raging across the territory. I mean, throw a dart at a timeline and you're gonna hit some Roman turmoil, but things were particularly bad during that period, and it meant a lot of attacks on Roman boats. With such a gentle descent to the seafloor, some researchers think that this merchant ship was deliberately sunk by its crew after something like a pirate attack to stop an enemy from seizing this extremely precious cargo. And if that's the case, we owe the crew of that ship our deep appreciation for their sacrifice, because nobody got their hands on that cargo until long after the fall of the Roman Empire. But it wasn't just modern archaeologists who wanted these ancient ingots. Researchers in a completely unexpected field also did, and those scientists hope to use them to solve one of the universe's biggest mysteries.
This SciShow video is supported by Babbel. Babbel is one of the top language learning apps in the world, with 14 different languages at your fingertips, including Italian, which comes in handy for this video. With Babbel's help, you wouldn't need us to translate mal di ventre into stomachache, because you'd know that already. Also, everything we learned from Professor Donatella Salvi was sent to us in an email written in Italian, so knowing multiple languages can come in handy when you least expect it. You can learn through a wide variety of lessons that prepare you to have practical conversations about travel, business, relationships, and more. There are also several subscription plans for you to choose from, including a lifetime subscription. And I know a lifetime is a long commitment, but you can cut that subscription short and get all of your money back in the first 20 days if you find out it's not your thing. And when you sign up using the link in the description down below, you can get up to 60% off.
According to our best theories of the early universe, we shouldn't actually exist. And by we, I don't just mean like you and me, I also mean like the Earth and the Sun and all of the other stars, and neon legwarmers and Kia Sorrentos and black holes and neutron stars, everything. This mystery is, of course, far older than any shipwreck. It all started shortly after the beginning of time itself, when the universe was in its Jessica Rabbit era, young and indescribably hot. The universe had expanded and cooled just enough to let some of its energy transform into matter and antimatter for the very first time. In an infinitesimally small amount of time, basically all of the stuff that would ever exist was born. But there's a problem. Like, whenever a particle of matter and its antimatter twin meet, they annihilate one another. In a literal flash of light, their mass gets converted into energy and rejoins the cosmic pool from whence it came. So if matter and antimatter are produced in equal amounts, which is what the laws of physics tell us, and they are destroyed when pairs meet up, the total amount of matter and antimatter in the universe should be none. But you may have noticed that's not the case. Otherwise, we wouldn't have hot dogs. From our observations of the universe, it appears the ratio of matter to antimatter was not exactly 1-to-1. It was more like 1,000,000,001 to 1,000,000,000. In other words, for every 1,000,000,000 matter-antimatter pair annihilations that happened in our baby universe, there was somehow one matter particle left over. And eventually, those leftover matter particles came together to make every single star and planet and YouTuber, author, CEO, sock salesman. That's me. But we do not know how or why this happened. It's one of the biggest outstanding questions in particle physics right now, and scientists think the answer could lie with some of the most elusive subatomic particles of them all. They're called neutrinos. You could think of them as cousins to a more recognizable subatomic particle, the electron, but unlike electrons, neutrinos don't have an electric charge. They're also way less massive, which is something because electrons aren't exactly hefty. Put these two facts together and you get a unique group of particles that almost never interact with other matter. In fact, as you are watching this, trillions of neutrinos are streaming through you without a single side effect. They can pass through an entire planet as if it isn't there. Now that means that there's nothing for you or I to worry about, but scientists have to worry about capturing them to learn how they work. So despite physics predicting that neutrinos existed about a century ago, we're still lacking some pretty basic information about them. Like, we still don't know how much mass they have, so I can't even tell you how many Kia Sorrentos they weigh. We know it's not nothing, but beyond that, it's kind of anyone's guess. Another big question is whether or not a neutrino can act as its own antiparticle. Now this is where we're gonna get a little more particle physicsy, so please stick with me. According to the standard model of particle physics, which is the theory that scientists rely on to understand the subatomic world, every matter particle has its own antimatter counterpart. For example, you got protons and antiprotons, electrons and anti-electrons. Each twin in a matter-antimatter pair has the exact same mass, but the opposite charge. Neutrinos, though, are neutral. So does that mean that they don't have antiparticles? No. Turns out charge is just one piece of the anti-puzzle. There are other properties that I had never heard of. Things like lepton number and helicity.
It's helicity.
Oh, it's helicity. And those are also opposite and antiparticles. So antineutrinos are very much a thing. In fact, don't look now, but your body is currently emitting antineutrinos. No, really, don't look. You won't be able to see them. Weirder than that, though. Back in the 1930s, an Italian physicist named Ettore Majorana hypothesized that a neutrino could act as its own antiparticle. Such dual-acting particles have come to be known as Majorana particles. If scientists discover that neutrinos truly are their own antiparticle, for reasons that get pretty complicated pretty fast, it could explain why our universe is filled with matter. However, Majorana's hypothesis was just that, a hypothesis, and he made it in the early days of particle physics. Although the field has made a lot of strides since then, it has not made much progress on neutrinos. But we finally may be on the verge of having proof that Majorana was right. Deep beneath the Apennine Mountains in central Italy, physicists created an experiment. Its name was Cuore, which is Italian for heart, but of course, it is also an acronym short for Cryogenic Underground Observatory for Rare Events. And part of Cuore's mission is to observe a hypothetical event in particle physics called neutrinoless double beta decay. Basically, there are a few ways that unstable atoms release particles on their way to becoming stable atoms. Most of these forms of radioactive decay are garden variety and well understood by physics, but neutrinoless double beta decay? Never been witnessed. And here's where you're gonna have to trust us on two things, because the science is intense. First, neutrinoless double beta decay would require neutrinos to be their own antiparticle. And second, neutrinos being their own antiparticle could have led to the accumulation of matter in the early universe. It is a multi-step process. I'm told that it's very complicated. Though, if any of you out there are craving an episode on leptogenesis and right-handed neutrinos and the seesaw mechanism, there is an internal debate going on at SciShow over whether we should cover it, so if you want to know, let us know in the comments. But remember, neutrinoless double beta decay itself is hypothetical. It's never been observed before, which means if it does happen, it's an extraordinarily rare process that needs an extraordinarily large and sophisticated experiment to detect it. So before Cuore was able to get up and running, scientists had to start with some early scaled-down proof of concepts. Basically, you'd need a lump of radioactive material and a detector that is sensitive enough to spot when antineutrinos are and are not present. So starting in the 1980s, experiments featured radioactive samples weighing just a few hundred grams. That's just a few Costco hot dogs. And over the decades, this got scaled up to over 700 kilograms inside the full-scale Cuore facility. For the radioactive element, the team went with tellurium-130, not only because it undergoes the kind of decay they needed, but because it does so with a really clear energy signature that will shine a beacon on any missing neutrinos. But it isn't one massive block of the stuff. Instead, Cuore houses nearly 1,000 Rubik's Cube-sized blocks of tellurium oxide crystals that have been arranged into 19 neighboring towers. It's a lot of weird units in this video. If neutrinoless double beta decay does happen, then, again for very complex reasons, the surrounding tellurium oxide cubes would heat up by a very small but very specific amount. And that is why each crystal has an extremely sensitive thermometer on the surface. It's also why each crystal needs to be kept at an incomprehensibly frigid temperature. And by incomprehensibly, I mean it's about 270 times colder than the depths of outer space. It is the coldest cubic meter in the known universe. Like literally, if there is a colder spot in the universe, it's because aliens made it. But the technique we use to create it is surprisingly simple. You know when you get a cup of coffee or like a bowl of soup that is just scalding hot and you cool it down by blowing over the top of it? Well, Cuore kind of does the exact same thing, except it isn't blowing air over the thing it's trying to cool down. It is blowing liquid helium. And with this technique, all of the Cuore cubes sit at a brisk 10 millikelvins, or negative 273.149 degrees Celsius. But temperature isn't the only thing that the experiment needs to carefully regulate. Cuore's radioactive cubes also need to be shielded from any external sources of radiation and energy, lest the extremely rare and extremely faint signal from a neutrinoless double beta decay event be completely overwhelmed by even the slightest amount of background noise. And this is the reason why the entire Cuore facility is located deep beneath the Apennine Mountains at the Gran Sasso National Laboratory. Around 1.4 kilometers of solid rock shields the experiment from the unceasing shower of neutrinos raining down from outer space. But even that isn't enough. Because here's something that you don't think about until it matters. Rocks themselves are slightly radioactive, which means the Apennine Mountains also slightly radioactive. So Cuore needed something to protect it from the protection it was getting from the mountain. It's like if you had a shield that also constantly stabbed you. Whether you are a fan of Superman or a person who has gotten your mouth x-rayed at the dentist, you are probably familiar with lead's use as a shield against x-ray radiation. But lead is good at radiation shielding, period, because it's just made of big, heavy atoms that cluster close together. That's why it's so heavy. That's why half your arm's worth of it weighs as much as a 10-year-old child or a German Shepherd or a 50th of a Kia Sorento. This means tiny particles find it very difficult to pass through even thin layers of this stuff, either just bouncing off the atom's nuclei or just getting absorbed by them. So it's no surprise to see lead lining everywhere from nuclear reactors to, yes, your dentist's office. But there's another problem. Just like a rock can be radioactive in trace amounts, so can a lump of lead. There are several kinds of non-radioactive lead, but there is a small but significant amount of a radioactive kind called lead-210 that is present in any that is mined from the Earth. And that stuff has a half-life of 22 years. Meaning, 22 years after you mine a lump of lead, half the radioactive stuff will be gone, and it takes another 22 years for half of that leftover half to decay, and so on and so forth. So any lead that has been mined in the last, say, 100 years will still have an appreciable amount of lead-210, which means that modern lead is simply too radioactive to provide shielding for Cuare's sensitive detectors. But lead from the ancient world is another matter. Lead that was processed by the Romans more than 2,000 years ago has had more than enough time to stabilize. And the stuff from an ancient shipwreck is even better because it spent all of those years underwater. Much like the Apennine Mountains protect Cuare from neutrinos and other subatomic particles raining down from space, the Mediterranean Sea protected the ship's ingots from cosmic rays that could strike the lead atoms and generate more unwanted radioactivity. This kind of lead is so valuable and in demand that physicists have a special term for it: low background material. But it's typically found in small quantities in things like anchors and isolated ingots. So not long after the shipwreck near Ventre was discovered, the Cuare team took a keen interest in the developments.
You may have noticed the very cool swimming astronaut shirt Hank is wearing, and also that I am wearing. Well, it's a reference to NASA's Neutral Buoyancy Lab, which we made an episode about back in June. The pool is so big, the water it actually looks blue. You can get one of these shirts for yourself at Complexly.store, the new home for merch from all of your favorite Complexly channels. And there is currently a summer sale happening. We've got up to 50% off items like a 3D printed kakapo from Bizarre Beasts, a false crab puzzle from Eons, and SciShow's very own Orca bucket hat. Sale ends August 23rd.
As fate would have it, the archaeologists who were trying to excavate the Ventre ship were struggling to bring it all up. With the boat and ingots sitting 30 meters below the waves, each diver could only spend about 30 minutes at the site before having to return to the surface. A project that began in 1989 hadn't made much progress in its first 2 years, and they needed more money. And that's when Italy's National Institute of Nuclear Physicists, which represents the Cuare scientists, approached Dr. Salvi's team with a proposition. In exchange for about 10% of the lead ingots on the ship, the organization of physicists would provide a cool 300 million lira to help bring up the ship's artifacts, which was about $210,000 at the time, which might not sound like a lot, but it would be enough to keep the dives going. Now, there was no getting around what these physicists were going to do with these ingots, though. They would melt them down and create shielding for their neutrino experiment. At the time, Dr. Salvi described the decision as, quote, painful, even though the physicists promised to claim only the worst preserved ingots and to assist in finding where they came from. The bars were, of course, irreplaceable. When an artifact gets preserved after archaeologists first analyze it, they can always return to it when they inevitably have further questions to ask or new techniques to apply. Once an artifact is gone, it's gone. And this was not the first time that physicists had sought low background material from historical finds. Over the years, they've used lead from several different sources, from old church roofs to the keels from ancient shipwrecks. Because the practice involves destroying ancient artifacts and can encourage illegal salvaging, it's become fairly controversial. The team behind an experiment called Cryogenic Dark Matter Search, for example, bought their low background lead from a company that had pulled it from an 18th century French shipwreck. But it turned out that salvage and sale wasn't entirely above board. The company wound up getting into trouble with French customs for the illegal trade of archaeological artifacts. And the United Nations Educational, Scientific, and Cultural Organization has condemned the recovery of shipwrecks for any commercial means. So yeah, you can imagine how torn Dr. Salvi and her team must have felt when the organization of physicists approached them with their offer. Ultimately, though, they decided to take it. The archaeologists were worried that if they took too long, the wreck might be plundered by less conscientious salvagers, in which case the artifacts would be lost to science altogether. Excavation resumed, and over the next 5 years, divers brought up hundreds of Roman relics. Most of the best ingots were moved to the Civic Archaeological Museum in Cabras. Some of them are still on display today, along with other artifacts from the wreck, so if you ever find yourself in Sardinia, go take a picture of them and send it to me, so I can see. And making good on their promise, the physicists helped analyze the lead ingots to confirm both where and when they came from. Lead from different parts of the world has subtly different compositions, which can be measured with precision instruments. And these lead ingots had compositions that placed their origins in the Sierra de Cartagena mines in southern Spain. So even though we will never know where the ship was heading when it sank, there is a solid chance that it left from Cartagena. And that might sound like Rome was engaged in a bit of international trade, but at the time, southern Spain was solidly under the control of the Roman Republic. So these ingots help researchers speculate that Rome preferred to extract ores from its foreign territories, in particular Spain, Greece, Britain, and Sardinia, rather than those within Italy. Perhaps this was to preserve their own supplies in the event of another civil war. At the very least, it appears they were focused on using the bulk of this lead themselves instead of exporting it to other foreign powers. And remember how I said that the names stamped onto the ingots tell us that the ship must have sunk sometime after 89 BCE? Well, archaeologists already knew that the Sierra de Cartagena mines were abandoned by 50 BCE. So unless someone allowed a bunch of surplus ingots to sit around being useless for years and years like a 2002 Kia Sorento, we now know the Mal di Ventre wreck must have happened between those two dates. Narrowing it down to a 40-year window 2 millennia ago is practically a pinpoint. In the end, the Sardinian archaeologists were happy with the deal they struck. Over the course of 7 years, they were able to excavate everything of archaeological value from the ship. But work for the Couore physicists had just begun. In 2011, they finally obtained 120 of the ingots, melted them down, and reshaped them into a 6-centimeter thick shield to surround their tellurium oxide crystals. Once everything else was in place, the Couore team began making their observations in 2017. The experiment required maintaining both the coldest cubic meter in the known universe and its exceptional radiation shielding for more than 5 years, with scientists monitoring the detectors almost constantly. If anything was going to find out the true nature of neutrinos and matter in the universe, this was it. In 2024, the Couore project published its latest results, and they were initially disappointing. After several years of observations, the team had failed to find any evidence of neutrinoless double beta decay. The hypothesis that neutrinos are their own antiparticle remained unproven, and physicists were no closer to solving the mystery of why our universe is full of matter. Every part of the experiment had worked perfectly, so this wasn't a result of any error or a fault in Couore's design. Instead, it was an indication of how rare this form of radioactive decay is, assuming it occurs at all. Just like with radioactive decay more generally, particle physicists describe the time it takes for neutrinoless double beta decay to happen using a half-life. And thanks to Couore, they now believe its half-life is at least 38 trillion years. For comparison, that's about 1,000,000 billion times the current age of the universe. Listen, I know even that can't help you that much. Maybe we could put it in terms of 10-year-olds, Kia Sorentos, Jessica Rabbits. It's a big number. But while that result isn't particularly helpful for solving whether or not neutrinos are their own antiparticle or answering why there's matter in the universe, it isn't like scientists have hit a brick wall with no plan to move forward. In fact, they're already transforming Couore into its own upgraded successor. It's called Cupid, or the Couore upgrade with particle identification. It's right, the acronym has an acronym as part of its acronym, and it is currently scheduled to come online in late 2024. So we really did go from Couore, meaning heart, to Cupid, the guy. Who said physicists aren't romantics? The most important part of this upgrade is swapping the tellurium oxide cubes out for blocks of lithium molybdenum oxide, which is a mouthful. But these new crystals will be easier to monitor for any signs of that neutrinoless double beta decay. Thanks to their different chemical makeup, the new blocks will produce a signal that, assuming it actually happens, should stand out a lot more against any background noise. And fortunately for archaeologists, upgrading Couore into Cupid won't require any additional ingots to bulk up the pre-existing pre-existing lead shield. But they might not want to celebrate just yet, because Cupid isn't the endgame, and neither is using Roman lead to hunt for one specific hypothetical form of radioactive decay. Kuore's lead shielding can be useful for plenty of other high-precision physics experiments, like the search for dark matter. Dark matter is like 5 times more abundant than regular matter and antimatter, and it helps form structures on both galactic and intergalactic scales, but physicists have basically no clue what it is. And lest you think the only people to benefit are theoretical physicists trying to explain the nuances of reality, Kuore's innovations may also find more practical applications, like in future generations of quantum computers. In other words, physicists are likely to need ancient lead from archaeological sites for many years to come. And while supply is an issue, a bigger problem might be an ethical one. Physicists certainly don't want to buy unethically sourced material, but it isn't always easy to trace the provenance of low background metals, as it was in the case of the Ventre shipwreck. And whenever there's demand, there's people looking to exploit it, leading to not just unethical, but full-on illegal salvage operations. It's clear that some formal resolution and guidance is going to be needed, something which archaeologists are actively pushing for. But while we wait to see if any official international laws get put on the books, we can look forward to the stories told from both fields. We can admire the Roman artifacts and let archaeologists paint us a picture of what life was like 2,000 years ago on the Mediterranean. From a foreign national who felt a jolt of pride stamping his name into a lead ingot, to a merchant sacrificing his boat so pirates couldn't profit from stolen cargo. And we can also await the results of Cupid and other particle physics experiments. Maybe someday soon we will finally solve the mystery of matter and explain how the entire universe as we know it came to be. Ancient Roman lead and all.